Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the second part of Chapter 5, the properties of conjugate direction methods. Now let's recall a little bit about conjugate direction method. So our aim here is try to solve the linear system AX equals B, where the coefficient A is positive definite. And we use the conjugate direction method, meaning that we update the iteration by the line search strategy, where the search direction is generated by the conjugate direction method, and the step length is given by the exact line search step, which has an explicit formula. With these settings, we can have some important properties. So before we discuss the properties, let's generate some figures to demonstrate how it works for the conjugate direction method. Now, here is a figure showing that if you got diagonal matrix A, then what is the coordinate direction works. Okay, so we start from the ending point, say x0 is here, and for A, where A is the diagonal matrix, we can move directly along the x-axis direction, and then we come up to the first x0 iteration. Then we turn up to search along the orthogonal direction, and using the exact step length, then we jump directly to the minimizer. In other words, for n equals 2, where the matrix is also a diagonal matrix, then we can actually search until the up to minimizer by 2 steps. Okay, so the algorithms will stop within 2 iterations. Okay, it means that we only need to search along the axis directions. Okay. However, if we got non-diagonal matrix A or a general matrix A, which is also positive definite, if we search along the coordinate direction successively, then we may not necessarily reach the local minimizer within 2 steps or finite steps, because in this case, the ellipsoid is no longer a circle, all right? So if we move from x0 to the smallest function value along this coordinate direction to get x1, then we move along the second direction to get x2. However, we're still far from the local minimizer, meaning that for this case, we need to do some transformation in order to have the finite termination properties. So what kind of transformation? Okay, so our aim is that we try to make this matrix A diagonal matrix, right? So we try to multiply A from left-hand side and right-hand side by a matrix to make A diagonal. This is possible by matrix theory, right? So this S is actually, we denote as P0 until P minus 1. Then by denoting this S, then we can make A to be a diagonal matrix. And after that, we can denote this new matrix X transpose AS to be the solution of the linear equation. Then we define X hat as the inverse of S multiplied by X. Okay, so the new function phi hat, X hat, which is the transformation problem by S multiplied by X hat, will have finite termination properties. Okay, so by doing this way, actually the new X hat is moving along the coordinate directions. However, from the x point of view, we are moving along the conjugate direction. Okay, so this is explained how conjugate direction comes. Now, let's do some preparations for the properties of conjugate direction method. So recall that we got the residual function rk as axk minus b. Somehow the difference between the left-hand side and right-hand side of the linear system. Then we can easily to verify that by the update of xk, we actually have the relationship of rk plus 1 with the previous rk. So this is the relationship that the difference of two successive residuals are alpha k multiplied by apk. Okay, so this is sort of residual update. Now, let's start from any point in n-dimensional space. And we generate the iteration xk by the coordinate direction method. Then we have the following result. So the result basically called the expanding subspace minimization result, which means that while we do the conjugate direction minimization, it's actually get the result like we expand the subspace minimization to the whole space minimization. Okay. Now, with the settings above, we have the following two results. The first one is that the residual function rk at the current iteration xk is orthogonal to all the previous search directions from p0 to pk minus 1. Okay, so all the previous conjugate search directions. The second result basically says that xk is the minimizer of this phi over the set. So this set, as we can see that it is starting from x0 and then plus by a subspace. This subspace is spanned by exactly the conjugate directions in the previous k steps, okay, from p0 until pk minus 1. So we try to prove this result. And the idea of our proof is as follows. Firstly, we will show that the two parts of the result, they are equivalent to each other. Okay, so in other words, if xk is the minimizer over the set, then it is equivalent to the first result. The residual at this xk is orthogonal to all the conjugate search directions in the previous steps. Okay, so this is the first step. The second step we will prove is that we only need to prove that this result holds. The first one holds. Okay, then after that, the whole theorem is actually proved as well. All right, so this is the way we try to prove the theorem. Okay, so now let's take a look at the first part. We try to prove that a point x star, it minimizes phi over the set if and only if the residual at this point is orthogonal to all the previous search directions from p0 until pk minus 1. Okay, so to show this, let's define a new function h about a vector sigma as follows. So this sigma is actually the coefficient in the following expressions. So phi, if we do phi as x0 plus sigma 0 p0 until sigma k minus 1 pk minus 1, then it actually means that the function of phi with respect to x theta, so x theta is defined from x0 plus the linear combination of the previous search directions, okay? Now, since x0 is fixed, and the first search direction p0 until pk minus 1 are also fixed, so the only variable here are the coefficient sigma 0 until sigma k minus 1. So we put them as a vector sigma, and then h is about a function of sigma. Now we substitute the h sigma to get the expression, and one can verify that h sigma is a quadratic function with respect to the variable sigma. Therefore, if we have to find the minimizer of h sigma, then h sigma satisfies the following result. The gradient of h with respect to sigma is 0. So in other words, for each component sigma I, we have the partial differential h about sigma I to be 0 at the optimal solution sigma star, okay? So by taking the gradient, we can actually show that this gradient is exactly the gradient of phi at sigma star transpose pi. So the gradient of phi is actually the residual function r at x star, okay? So by doing this, we actually means that if we get a minimizer about h sigma, and the minimizer is exactly the minimizer of phi, right? So phi reaches the minimizer if and only if the residual function is orthogonal to all the previous such conjugate directions. Okay, so this gives the first step. Okay, the two parts of the theorems, they are equivalent. Now, let's talk about the second part of the result. We try to show that the residual function at the current iteration xk is orthogonal to all the previous such conjugate directions. Okay? So to show this, we use the induction way, meaning that we first assume that the induction hypothesis holds for I from 0 until k minus 2, which means that this result holds for k minus 1, and we only need to prove that when this result comes to k, then it holds as well. All right, so this is the induction way to show the proof. Now, let's take a look at the proof, how it works. So recall that we have some successive relationship between the residual functions rk and rk minus 1, and we have that pk minus 1 transpose rk, they can be further rewritten as a inner product of pk minus 1 transpose rk minus 1 plus a second term. Okay, so if we take a look at the second term here, it actually somehow the pk minus 1 transpose a pk minus 1. Okay, so by the definition of alpha k minus 1, recall that the definition of alpha k minus 1 is that it is sort of ratio, and the coefficient, the numerator, okay, so the numerator is minus rk pk minus 1, and the denominator is actually this part, pk transpose a pk, right? So by the definition of alpha k, we can show that this term is 0. Then next, we only have to show that the residual function at the current iteration is orthogonal to all the directions from P0 until Pk minus 2, okay? Because we already showed that Pk minus 1 is orthogonal to Rk already. So the left part is we show this result, okay? So we show that for I from 0 to k minus 2, Rk also orthogonal to them. So how can we prove this? To show this, we also use the successive relation between Rk and Rk minus 1. So we substitute the relationship of Rk by the expression of Rk minus 1 here. So we get the expression here. And now for the right-hand side of the equation, the first term actually is 0 by our induction assumption, okay? So recall that we assume for k minus 1, we got this orthogonality condition, right? So this part is 0. And the second part is also 0 as well, because we assume the conjugacy of pi. Okay, so therefore the second part is 0 as well. By doing this, we get the residual function Rk at this iteration is orthogonal to all the search directions from P0 until Pk minus 2, and together with this exact step length direction, Rk is also orthogonal to Pk minus 1. Therefore, we have showed that for k iteration, the result also holds. So by the theory of induction, we actually proved the first part of this theory, okay? So in other words, for conjugate direction method, it has a very nice property that we minimize the problem for each directions, okay? It is equivalent to we minimizing the problem along all the k-dimensional subspace, all right? So it is a very nice property. Okay, now let's make a brief summary about this part. In this part, we mainly discuss the nice property of conjugate direction method, which means that when we search along each conjugate directions by exact line search for solving a quadratic function minimization problem, it is equivalent to solving the minimization problem within n-dimensional subspace. Okay, so it is very nice properties. Now, we stop this part here and see you next time.